Hello, I'm Troy Sanders, and today I'll be doing a presentation on density and specifically in crystalline structure. So just to give an overall description of density, density is the degree of compactness of a substance, and it can be measured by the mass of a substance over its volume, or you could just simply say the equation density equals mass over volume. And then common units of density are grams per centimeter cubed and grams per milliliter. And then other ones are kilograms per meter cubed and kilograms per liter. And density varies among crystalline structures. The specific ones we're going to be covering are body center cubic, face center cubic, and hexagonal closed pack. And then there's a lot of products in the real world that are selected based on their densities because of the properties of products that density impacts. So there's some common measurements of density, starting off with linear density, which would be the number of atoms per unit length in a given direction vector. And then you can see by that equation, it's the numbers of atoms that are centered on the direction vector over the length. And that will give you a unit of nanometers to the -1. And then there's also planar density, which is the number of atoms per unit area centered on a specific plane, which is number of atoms centered over the area. And then there's volumetric density, which is the most common measurement of density, and that's used in like regular calculations for substances. As you can see, this goes in order from length to area to volume. So some terms to know for density calculations are the atomic packing factor, which is mainly used for crystalline structures, and this takes into account the volume of the atoms in the unit cell over the total volume of the unit cell. And what it's really saying is what's the ratio of atoms to atoms into empty space. And this is kind of just a general number you can use for determining how packed a crystalline structure is. Then for other calculations, you'll want to know the atomic radius, which is the radius of each atom in the unit cell edge length, which you can use to calculate the densities and volume, interior atoms, face atoms, and corner atoms, which you can see their use in the equation below, which is used only for volume. And the values will differ if you're calculating linear and planar densities, which we'll get into. So there's 3 types of crystalline structures I'll be covering. There's body center cubic, which is the least compact, as you can see by both the atomic packing factor and the equation for atoms inside the cell. There's the face center cubic, which is equally as packed as the HCP, hexagonal closed pack. And the reason it's 4 atoms per unit cell versus 6 atoms per unit cell has to do largely with the shape. The hexagon is obviously bigger than a cube, and if you notice, you have to use a C to A ratio because you can't calculate volume just with the A value for this one. So going on, I got a 3D model of molybdenum. So just to calculate the volume real quick and get into the unit cell edge length. So for the unit cell edge length, you do 4R over the radical of 3. The radius for molybdenum is 0.1363, so you just plug that into the A, and then you cube this value here, and that gives you the volume. So moving on to the linear density, first you have to get a direction vector, and this one chosen was 1, 0, 0, so that would start from the origin where the line starts and move there. The reason it's in the half of the atom is because the unit cell is a sliced version of this. So then for your radius, you get 0.1363. You figure out your unit cell edge length, and then you determine that one atom is centered because you have 2 radii. So that would just equal 1 full atom. And then you just divide 1 by the 0.3148, and you get your linear density, which is in nanometers to the -1, as you can see, because it's 1 over nanometers. Moving on to the BCC, so I chose the 1, 0, 0 plane again. As you can see, it's in the corner of the atom, and you find the area by squaring the value you found for A previously, and you get a value of 0.0991. And then you can see that there's 4 corner atoms centered on this plane. So 4 corner atoms would make 1 full atom centered on the plane. And then you would divide 1 by the area, and you get 10.09. And it's nanometers to the -2 again, because you got a nanometer square on the bottom. So I'm just going to go into the importance of density in real-world examples now that we've discovered it, or dug into it. And one is for the flotation of objects. So if you want to make anything like a boat or just a product that floats, the density of what you're making has to either displace more water than it weighs or be less dense than the fluid it's in. Additionally, it gives you easy estimation of products when you're given the volume and densities, or 2 of the missing parts from the equation. Additionally, a cool thing is you can identify a material that you're not sure what it is by the element when you're given a mass and a volume, because you can look at like a reference table and see what its density is close to. Additionally, as I touched into, it's important in the material selection process for properties such as temperature and pressure mainly. So if you're dealing with a product that's going to go into high temperature or pressure environments, you'd want to have it with the density for whatever factors you want. And then lastly, if you're creating a liquid or gas product that you want to be in immiscible layers stacked on top of each other, it's important to know what their densities are. A common, just basic example of this would be like water and oil. Obviously, the oil would be on the bottom because it's more dense than the water would be on the top. And then I'll open it up to questions and answers now.